Imagine we had a random variable x that had a binomial distribution with n equals 10 and p equals 0.3. So recall that p is the probability of success. And given these parameters, we could solve any probability like this, where we're seeking the probability x is less than or equal to some value of a, which is just the cumulative distribution function of x evaluated at a, which is going to be the sum starting from 1 to a of n choose the index we start off from times the probability of success to the index power times 1 minus p to the n minus our index. And given these parameters, all we have to do is just plug in what we have. So if we were looking for the probability that x were less than or equal to 3, then this would just be the sum from 1 to 3 of n choose I times p, which is 0.3, to the power of our index times 1 minus p, which is 0.7, to the, so n would be 10, times 0.7 to the 10 minus the index. And we could solve this expression and find this probability. Now, what if we had a random variable x where we have a certain number of trials, let's say n equals any number of trials, let's call it a, but we didn't know what the probability of success was. So what if p is unknown? That's a problem because if the probability of success is unknown, then we won't be able to solve a probability like this because we require p in order to solve this equation. And this is not just a problem for a binomial distribution. There are other distributions where parameters may be unknown. What if x were normally distributed, and we know the parameters of a normal distribution is the mean and the variance, and it could be the case that both mu and the variance are unknown. And so we can't solve any probability like this. We can't solve this. So this is unsolvable if we don't know, or if this occurs, if the mean and the variance are unknown. So how do we solve this problem? What can we do? Well, there's a method from statistics that allows us to at least estimate these unknown parameters. And what we call these unknown parameters in general, we'll give it a name, we'll call them theta. So any unknown parameter in our distribution will be denoted by theta. And theta can either be one value, two values, or infinitely many values. So if we go back to our example here, our theta is going to be just p because p is unknown. And in the case of the normal distribution, our theta is going to be mu and the variance, where mu is the mean. And the way we list that out is as a vector of points, where the first one is our mean and our second is the variance. And if we had a distribution where n parameters were unknown, then our unknown parameter theta would be a vector of n unknown parameters, and so on. When we have an unknown parameter, we need to denote that in our probability mass function or probability density function. If x were discrete, then the probability mass function, the PMF of x, would get denoted like this, where we separate the variable and the unknown parameter by a semicolon. And if x were discontinuous, then the probability density function, f of x, would get denoted similarly like this. As an example, if we had a random variable x that were Poisson, and let's say we knew what the mean was in advance, so we knew what the mean was, then the probability mass function of x would just be our mean to the power of x times the exponential to the negative mean power divided by x factorial, where x equals 0, 1, 2, etc. But if the mean was unknown, then we would replace small gamma with the theta symbol, and the PMF would look like this. So it would be theta to the x times e to the negative theta divided by x factorial with the same domain. And of course, the PMF is equal to 0 elsewhere, where x does not equal any other value from this domain. With unknown parameters, as we talked about, probabilities such as this, if x is binomial, or this, when x is normal, are unsolvable. And we want to find a way to calculate these probabilities at least approximately. And the way we can do that is by estimating the unknown parameter. If we could find a method to find a great estimate of our unknown parameter theta, then these probabilities will at least approximately be equal to the actual probabilities if we had known what the true parameter is. But in order to understand the method of estimating such parameters, we need a few definitions. And the first of them is a random sample. So a random sample is going to be this. It's going to be a collection of n random variables, let's call them x1, x2 through xn, which basically will come from the distribution. So they come from the distribution of some random variable x, which means each of these random variables will have the same distribution. They'll have an identical distribution. Moreover, we also require that each of these random variables are mutually independent. So the sample is going to be independent. And the combination of them being identically distributed and independent is what makes it a random sample. Usually this gets abbreviated into just IID. So this random sample is identically and independently distributed. So if X were exponentially distributed, then that means every single random variable in this collection, if it's a random sample, will also follow an exponential distribution with the same parameter. And them being independent means that we could easily find the joint probability density function of this collection, because them being independent implies that the joint probability density function, let's say if it were continuous, of x1, x2 through xn would just be the product of each of their marginal PDFs. So it would be the product of their marginal PDFs, which is pretty neat. And that's basically what a random sample is. Random sampling will help us estimate the unknown parameter. And this estimate will eventually be called a statistic. And a statistic is a function. So a statistic is going to be a function of the random sample. Okay, so how does that look like? So we denote a statistic by theta hat. So this caret symbol will be called a hat, and we have a theta under it. So this statistic is going to be a function of the random sample, which is going to be the input of our function, right? So our random sample is going to be the input of this function. And given a set of values for x1 through xn, so given some values of x1 through xn, which are called the realized values, they're called the realized values, we can then calculate what the statistic actually equals, what its true realized value is. Let's take a look at a special example of a statistic. We have a special statistic that's called the sample mean. And the sample mean is going to be, as a statistic, a function of our random sample, which is going to be defined as the sum from the first to the last random variable divided by the number of the total random variables in the random sample. So this statistic will be quite important when we seek to estimate our unknown parameter theta. Here and here. And if we were actually given some values for this, we will be able to calculate this statistic. So suppose we had x1 were equal to 7, x2 was equal to 1, x3 was equal to 3, and x4 equals to 10. And this was our random sample of size 4, then we can calculate this statistic by what is defined. So x hat, which is the sample mean, is a function of these values. So x1 is 7, x2 is 1, then 3, and then 10. And putting these inputs in the sum means we're doing 7 plus 1 plus 3 plus 10 divided by 4. And this equals 5.25. So the sample mean, or the sample average of this specific collection of realized values is going to be 5.25. But in general, the sample mean will just be this.